In today's lesson, we are going to be talking about some of the applications of Taylor and Maclaurin polynomials. We have memorized the series for sine x, cosine x, and e to the x. We can use our memorized series, our memorized Maclaurin series, for these functions in some other functions, some variations of sine x, cosine x, and e to the x, if their arguments, what I say, behave the same as the known series does, arguments do. All right? For instance, let's consider this one. F of x is cosine of 4x centered at 0. So we have memorized the series for cosine x centered at 0. Right? We have memorized that one. So as x goes to 0, the argument goes to 0. As x goes to this thing, this argument goes to 0, right? Well, if there's a 4x centered at 0, what does this argument do as x goes to 0? It goes to 0 as well. So both arguments go to 0. When that's the case, we can use, okay, let me do this. 4x goes to 0. Okay, if their arguments behave the same at the center value, then we can use the memorized series for cosine to immediately get the series for our new function, and without having to go through all of the derivative process. So our series for cosine is 1, starts with a 1, and then we alternate signs, so minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. Yeah? So cosine of 4x is the polynomial at 4x. So we are going to take every x and replace x with 4x. I like to think of it like that. Replace every x with 4x. Okay? So the 1 stays a 1. There's no x in it. Minus, I'm replacing that x with 4x. I'm replacing this x with 4x. Oops, minus. I'm replacing this x with 4x. And it goes on and on. So I could rewrite this if I wanted to or needed to as 4 squared x squared over 2 factorial plus 4 to the 4th x to the 4th over 4 factorial, etc. if I needed to or wanted to. Okay? So that's what I mean about you can use your memorized Maclaurin to create a Maclaurin for a new function without going through the whole derivative process. Okay? But that only works when their arguments behave the same. Let's look at another one. We're going to write a 7th degree Taylor polynomial for this function centered at x equals pi over 3. So as x approaches or goes to pi over 3, what does the argument do? So x minus pi over 3 does what? What does it go to? Well, if I put pi over 3 in for x, this whole thing is going to 0. Just like the Maclaurin for plain old sine x does. So this argument behaves like the other argument does. At the center. At the center. So I know the Maclaurin for sine x. Sine x starts with x. And then we alternate signs. X cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus dot dot dot. Yeah? So the Taylor polynomial centered at pi over 3 will be sine of x minus pi over 3 centered at pi over 3 will be, I'm going to replace every x, I'm going to write this down, replace every x with x minus pi over 3, because that's what we're doing. So replace this x with x minus pi over 3. Replace this x with x minus pi over 3. And keep on going. And now, I almost put plus dot dot dot, but you don't want to put plus dot 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 because it says we need to find a 7th degree Taylor, so I need to stop at 7. If you keep on going, it's no longer a 7th degree polynomial. So we're going to stop right there. Do not even write the plus dot 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 because that says you're going. And if you go further, it's no longer a 7th degree polynomial. Let's do another one. We're going to find a 6th degree. So we'll need to remember to stop at 6. Find a 6th degree Taylor for this function centered at c equals 0. So as x goes to 0, I'm doing that because of this here. Just like here I did the x is pi over 3. Oops. Okay. As x goes to 0, what does the argument do? What does x squared over 3 do? Well, it goes to 0 just like the argument in e to the x goes to 0 for the Maclaurin. So it checks. When these check, you can use your memorized. If they don't check, then you must go through the whole derivative process. So e to the x starts with 1 and is always positive. The next term is x, and then x squared over 2 factorial, x cubed over 3 factorial, x to the 4th over 4 factorial, and it keeps on going forever. Okay, we want e to the x squared over 3. So we will replace every x with x squared over 3. So 1 plus x squared over 3 plus, I'm replacing this x with x squared over 3. So x squared over 3 squared over 2 factorial, right? Plus x squared over 3 cubed over 3 factorial. Now, I was about to write another one. However, we need to stop at the 6th degree term. And I'm already there because when I have an x squared cubed, that is x to the 6th. So we stop right there. Okay? This would be a safe stop spot. Nothing wrong with stopping right there. But as a multiple choice question, this would be 1 plus x squared over 3 plus, they would write this as x to the 4th divided by 3 squared times 2 factorial. Okay, I'm multiplying top and bottom by 3 squared to get that 3 squared in the bottom here. Plus x to the 6th over 3 cubed times 3 factorial. And no plus dot dot dot, it stops right there. Okay? So if it was multiple choice, this is how they would do it. Also, you guys, if you were doing something further with this, later on we're going to be taking the derivatives of this or the integrals of this. So if you're doing something further, it's going to be helpful to you to write it like this. Don't leave it like this if you have to do something further with it. Safe stop, and then simplify it. Okay? Number 3. Find a Maclaurin series. Find a Maclaurin series for f of x is cosine x. Then use it to approximate the value of this integral so that the error in your approximation is less than 1 over 1,000. Okay, well, first things first, they tell me to write the Maclaurin series for cosine x. Not a problem, I have that memorized. So cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. Keeps on going. Okay? Now I'm going to use this to approximate the value of that. Okay? Now I will note that as this is written, I would not know how to integrate that. I really would not. I'm looking at it with just the eyes of integration, and I don't know how to integrate that. But with series, it's going to be pretty easy. Okay? So I'm going to rewrite this integral using our approximation for cosine. So this will be the integral 0 to 1 of 1 minus, I am replacing cosine x with that infinite series. So I'm just going to rewrite this. Okay. All divided by x squared, and I'm integrating with respect to x. Okay, I'm going to clean up the top because I have 1 minus 1, and then I'm distributing the negative through the rest of the terms. So I'm going to rewrite this integral as, also I'm dividing by x squared. I'm going to write dividing by x squared as 1 over x squared. I'm going to write that out in front, just make it look nicer on my eyes. It's purely for myself. Okay, the 1 minus 1, I have no 1's left, but then the negative is going to distribute, and I'm going to have a positive x squared over 2 factorial, then a negative x to the 4th over 4 factorial, a positive x to the 6th over 6 factorial. I might go ahead and write the next term here, get at least 4 terms here to give me a good pattern, and then plus dot dot dot. Still with the eyes of cleaning this up before we integrate, I'm now going to distribute 1 over x squared to each term. For the first term, I'm going to be left with 1 over 2 factorial. For the second term, I have minus x squared over 4 factorial plus x to the 4th over 6 factorial minus x to the 6th over 8 factorial plus dot dot dot. Okay, and now we integrate. So we integrate, and all these are our little polynomials. So each of these is just a power rule. So the integral of 1 over 2 factorial with respect to x is just x. Well, 1 over 2 factorial x, or x over 2 factorial, minus raise your power by 1, divide by your new power, plus raise your power by 1, divide by your new power, minus raise your power by 1, divide by your new power. And that would keep on going, and now we're going to evaluate that from 0 to 1. If you put 1 in for every x, we will get just 1 over 2 factorial equals, okay, minus 1 over 3 times 4 factorial plus 1 over 5 times 6 factorial minus 1 over 7 times 8 factorial plus dot dot dot. If I put 0 in for every x, everything has an x in it, and that's just going to be 0. So this is the value, this is the infinite, I mean this is the exact value of that integral, okay? We only want to approximate it so that our error is less than 0.001, so 1 over 1,000. And I noticed that this series is alternating in sign, and its terms decrease in magnitude to 0. So I know that the error in using, if I only used the first term, the error would be the absolute value of the second term. If I use the first two terms, the error would be the absolute value of the third term, etc. So which of these terms is less than 1 over 1,000? Which of these is? Well, the first term is not less than 1 over 1,000 because the first term is a half. The second term, 3 times 24. Well, 3 times 24 is not 1,000, so not that one. The second term is, or the third term is 5 times 720. And 5 times 720 is indeed bigger than 1,000. So this is our error term. So I can say that this integral is approximately equal to 1/2 minus 1 over 3 times 24, 4 factorial, with an error less than or equal to 1 over 5 times 720. Not too bad, not too bad. Let's see how close we are. So I still had this on there from yesterday. Okay, first of all, let's find our approximation. So our approximation was 1/2 minus 1 divided by 3 times 4 factorial 24. So there is our approximation for this integral. Now let's find the calculator's approximation for the integral. Math 9, 0 to 1. I might just make it look like it says here. So 1 minus cosine x divided by x squared dx. So not a bad approximation. 2 terms was all it took to have our approximation have an error of less than 1 over 1,000. Not bad. If we had done one more term, we would have gotten a better approximation. Yeah? So that is the power of these Maclaurin series and the Taylor series. That's the power of them. They can approximate these. And I don't know if it's still the case, but there was a time when these calculators, every calculator, you know, there's not a little man in there integrating, yeah? So they actually use Taylor series to get this answer. They just do a lot more terms until whatever tolerance is programmed into the calculator is reached. Once the tolerance has been reached, then it stops and it gives you the value. That's why sometimes when we know, like I know that maybe an answer is 1/3, but they would give me like 0.333333217 or something like that. So their tolerance has been reached. It's not exactly the answer because they are using a numerical method to get their answer.